So let's talk about the other four trig functions. You know the ones. They always seem to show up right when you think you finally got a handle on sine and cosine. But here's the thing. Graphing them doesn't have to be this big, complicated mystery. The secret is actually a technique you already know, and we're going to unlock it right now. And yeah, I get it. These graphs can look pretty wild, right? You've got these weird breaks, these swooping curves, and none of that familiar, gentle wave pattern that we're used to with sine and cosine. It's really easy to feel like you're starting all over from square one. But you're not. You're not starting over at all. The truth is, all four of these functions are really just sine and cosine wearing a disguise. Seriously. If you can sketch a basic sine or cosine wave, you have basically everything you need to absolutely master these other graphs. Let me show you how. So here's our game plan. We'll start with a foundation, then I'm going to show you two super simple tricks, one for the reciprocal functions, one for the ratio functions. Then we'll use those tricks to tackle a more complex example and finish up by working backward to figure out a mystery graph. Okay, first up, beyond sine and cosine. Look, everything we're about to do is built on one really simple idea. Sine and cosine are the absolute bedrock of all of this. Let's see just how they create the foundation for everything else. All right, let's kick things off with secant and cosecant. The trick here is to think of their parent functions, sine and cosine, as a kind of scaffold. It's like a helper graph that we're going to build the real graph on top of. Let's start with secant. As you can see, secant of x is just 1 divided by cosine of x. Now, think about what that means. When the cosine wave is at its peak, at 1, well, 1 divided by 1 is just 1, so secant is also 1. But when cosine gets really close to 0, dividing by that tiny number makes the secant value shoot up towards infinity. And when cosine is exactly 0, well, that's where things get really interesting. The method for this is actually beautiful because it's so simple and you can do it every single time. It's just 3 steps. First, you're going to lightly sketch your helper graph. For secant, that's cosine. Second, find every single spot where that helper graph hits 0 and draw a vertical dotted line. That's an asymptote. And finally, you just draw these U-shaped curves that kind of spring off the peaks and valleys of your helper graph. That's it. Okay, let's build one together right now. We'll start by just rightly sketching the graph we all know and love, a simple cosine wave, starting at its peak when x equals 0. This is our foundation, our scaffold. Next up, find every spot where our cosine wave hits that 0 line. Now remember, secant is 1 divided by cosine, so trying to calculate secant right at these points would mean dividing by 0, which you can't do. It's impossible. So instead, we draw these vertical lines, these asymptotes. Just think of them as electric fences that the graph can get really, really close to, but can never actually touch.
And now for the final touch, the fun part. From every peak of our cosine wave, we're going to draw a U that opens up. And from every valley, or trough, we draw one that opens down. You'll see these curves get closer and closer to those asymptotes we just drew, and just like that, you've graphed the entire secant function, all by using cosine as your guide.
All right, let's switch gears. Now we're going to look at tangent and cotangent. These guys aren't reciprocals, they're ratios. But the secret to figuring them out, it's exactly the same. Just break them down into their sine and cosine parts. So the tangent function is just sine divided by cosine. And what that means is that all of its key features are totally predictable. The graph is going to be 0 whenever its numerator, sine, is 0. And it's going to have an asymptote, one of those breaks, whenever its denominator, cosine, is 0. Now, take a close look at this table. It shows this really cool, beautiful inverse relationship between tangent and cotangent. Notice how for tangent, the zeros happen when sine is 0. But for cotangent, that's where its asymptotes are. And it works the other way too. Where one graph has a 0, the other one has a break. They're like perfect mirror images of each other's behavior. It's pretty neat. And here is one really crucial difference you've got to remember. While sine and cosine, they need a full 2 pi rotation to complete one cycle, tangent and cotangent repeat their pattern every pi units. Why? Well, it's because their values depend on the ratio of sine and cosine, and that ratio repeats its pattern of positive and negative signs twice in every full circle. This gives them a much faster, more frequent cycle.
Okay, so we've got the basic shapes down. Now let's put our helper graph trick to the test on a function that's been stretched, shifted, and flipped. The kind of thing you'd actually see on a test.
So here's our challenge. Graph the function you see right there. I know, with all those numbers and shifts, it looks pretty intimidating. But what's the core rule we've been using? Well, cosecant is just the reciprocal of sine. So the key is to just ignore the cosecant part for a second and focus on graphing its much friendlier sine-based helper function first. So our helper function is y equals -2 sine of x minus 1 plus 1. We can just break this down piece by piece. That 2 out front, it tells us the amplitude is 2. The negative sign, that means the whole wave is reflected vertically, flipped upside down. Inside the parentheses, the -1 shifts the whole graph to the right by 1 unit. And finally, that +1 hanging on the end moves the entire graph up by 1.
And here it is. This is our helper graph. And even though it looks a little complicated, this wave gives us the exact blueprint for our final answer. Its peaks and its troughs, those are going to be the anchor points for our cosecant curves. And the spots where it crosses its new midline at y equals 1, yep, you guessed it, that's where our asymptotes are going to go. Okay, for our final challenge, let's flip the script. Instead of making a graph from an equation, let's try to find the equation from a finished graph. And the trick? You already know it. Spot the hidden helper function. So take a look at this graph. It's a series of U-shaped curves. It's pretty clearly either a secant or a cosecant function. But which one is it? And what kind of transformations has it gone through? The trick here is to just work backward. Let's sketch in that helper graph by basically connecting the dots. We'll touch the bottom of each of the upward curves and the top of each of the downward curves, and look at that. A perfect, familiar wave just appears. And since it starts at a peak right on the y-axis, we know our hidden helper has to be a cosine curve. So now we can just analyze this helper wave. First, let's find the midline. It's halfway between the peak at y equals 1 and the trough at y equals -5. So that's at y equals -2. That's our vertical shift. The distance from that midline up to the peak is 3 units, so our amplitude is 3. The wave starts at a peak at x equals 0 and finishes one full cycle at x equals 4, so the period is 4. Now to find the b-value, we just calculate 2 pi divided by the period, so 2 pi divided by 4 gives us pi over 2. And since it starts right at its peak on the y-axis, there's no horizontal phase shift to worry about. All right, let's put it all together and build our equation. We know the helper was a cosine curve, so our mystery graph has to be its reciprocal, which is secant. We found the amplitude was 3, our b-value was pi over 2, and our vertical shift was down 2. Put it all together, and you get the final equation y equals 3 secant of pi over 2 times x minus 2. We just decoded that whole mystery graph by finding the simple shape hiding inside of it. So I guess the real takeaway here is that complexity, a lot of the time, is just simplicity stacked on top of itself. Once you learn to spot these hidden scaffolds and the underlying patterns, problems that look really intimidating suddenly become manageable. It kind of makes you wonder, right? What other complex ideas out there are just simple foundations stacked together, waiting for us to see them clearly?